SwayamPrabha. Digital India. Educated India.
What do we mean by these models, and how do we get them, and what do we use them for, right? So that's something which we need to understand. So once again I am revisiting our idea of what we mean by a system, right? So for us a system is a mapping between u of t and y of t. Now suppose if let me call this as problem 1. Okay. The first problem I want to solve is that given u of t and y of t, we are asked to find the mapping S, okay, that relates the input u of t and the output y of t. Okay. This problem is what is called as the problem of synthesis. That is, suppose let us say like see, for let me take an example of a room that is being air conditioned, right. So let us say if I take the example of a room that is being air conditioned, then suppose if I want to regulate the temperature of the room, right. So the temperature of air in the room is the output of the system, and let us say the input to the system is the amount of cold air, okay, that I blow into the room. Okay. So let us say like let us look at this. Let us say we have a room air conditioner, right. So let us say the temperature of air in the room is my output, and let us say the amount of cold air provided, right, to the room through the AC vents is the input to the system. So what would this synthesis problem entail? Like the problem of synthesis essentially means that I provide varying quantities of the input to the system, and then measure the output and try to get a mapping between the two. Okay. So that is what I do, so that I get a mathematical model for the system. So in this case, like if I provide various amounts of cold air to my what to say air conditioner, and I measure the corresponding temperature and I get a relationship between the two, so then I will know how temperature of air in this particular room would vary, like as I provide varying amounts of cold air, right. So that is something which I will know. So once I do this first problem of synthesis, I can go and do problem number 2, which is going to be the following. Given the mapping S, once we find the mapping S and given a particular input u of t, find y of t. Suppose I have got a mathematical model for temperature of air in this room, right, equipped with an air conditioner. So tomorrow let us say like I want to essentially change the air conditioner, right. So and let us say I have 5 choices. So I know like what is the capacity of what to say blowing cold air into the room of all the 5 ACs, right. Without even purchasing them, I can use the model which I have developed to figure out how temperature would vary and settle down to a desired value by doing this analysis, right, once I have the mathematical model for this particular process of air conditioning. So the advantage is that like I can predict the temperature variation without even essentially the requirement of buying the air conditioner, installing it and testing it, right. So that I can make a well informed choice, right, as far as which AC to buy. So this problem is what is called as the analysis problem or the prediction problem. Okay. So that's essentially the analysis or the prediction problem. Okay. So and let us say we have looked at these two problems. Like another problem which we can do once we complete the synthesis problem is that given the mapping S and a desired output y of t, find u of t. Okay, that is the third problem that we can solve. So this problem is what is called as the control problem. Okay. So what do I mean by this? Like suppose let us say I come into a room with an air conditioner. I essentially want to what to say regulate the temperature of air in this room, right. So I set the temperature of air as 25 degrees Celsius. The question is that like what is the amount of cold air which I should blow, which would get my temperature to 25 degrees Celsius, right. That is the problem of control. So I know what is the mapping of the dynamic system, and I want a desired output. What is the input which I have to provide? Okay. So in a certain sense it is the inverse problem of what we do in problem number 1, right. So here like or inverse of what we do in problem number 2, right. So so this mapping helps us to find a y of t given a u of t. In the problem of control what we do is that like given a y of t, like I want to use this mapping to find what u of t will get me the output y of t, right. So that is the problem of control. Okay. So what are a few examples of control like that we can essentially look at. Like we have already looked at like room temperature control, right. So that's one example that we have discussed, right. Let us say like we have also looked at an example where we want to control the motor speed of a motor, right. Okay. And our human body is a marvelous controller. See for example like our human body maintains our body temperature in a very narrow band, right. So even like if the temperature goes to 100 degree Fahrenheit, right, so we are in trouble, correct. So so essentially our body maintains our internal body temperature like in a very narrow band irrespective of what that environment temperature is, right. So it does not matter whether we are in winter or in summer, the human internal body temperature is maintained at almost a constant value, and that is a great control system, like. And for example the blood pressure like that is maintained by a body, it should be in a good range. Blood sugar levels, right. So that is another marvelous control mechanism. And in fact like even our heartbeat, right. So even our heart, which is a pump, essentially that pumps like blood throughout the body, like it needs to work repeatedly again and again, right. So for like as far as we live, right. So that is extremely important for us, right. So our human body is filled with marvelous controllers which regulate various variables like around desired values very accurately and for a long time, that is something which is marvelous, right. So so essentially we are going to look at various case studies as we go along, and then like we will see how to formulate practical problems as a control problem and solve them. Okay. So before we what to say get into the mathematics, I just want to give more another physical perspective as far as what we what to say how we classify, how we look at control and so on, right. So essentially in a very broad sense people classify control as what is called as open loop control and closed loop control. So what are these terms? So let us say we consider the example of a ceiling fan, right. So if I have a ceiling fan, what is going to happen? I have a fan, I have a regulator, I have a switch, right. I can come switch on the fan and I can vary the speed setting maybe in discrete what is it quantities by using the fan speed regulator, and that is about it, right. So I just get some output which is a fan RPM. Okay. So that is an open loop controller in the sense that like it cannot account for any disturbances, right. So, which come during the operation of the fan. See, for example, if there is a voltage fluctuation, right, then like the output of the fan or the speed of rotation of the fan is going to fall down, okay, or go up depending on whether the voltage is falling down or going up, all right. So, then like the question is that like I lose certain performance, right, but the question we need to ask ourselves is that like is it important for a ceiling fan, right. So, typically ceiling fans are open loop control systems where the speed settings are calibrated in the factory and the regulator essentially adjusts the what to say fan RPM in discrete what to say in a discrete range of values, right, set of values. And essentially in the presence of disturbances, obviously the system response gets affected, right. So, that is a what to say characteristic of open loop control, okay. So, open loop control means like what are the various what to say characteristics. There is no feedback, we will shortly define what is called as feedback, okay. So, as a result there is no feedback in open loop control. So, essentially it cannot tolerate disturbances, okay, it is not robust to disturbances and so on, okay. But on the flip side the cost and complexity are lower. On the other hand, suppose like if we want a fan like whose RPM needs to be maintained at a what to say very baseline value, let us say 100 RPM, right, and I cannot afford a huge variation in the RPM, right, for some industrial application, right. What would I do? What I would do is that like I would measure the actual RPM using a speed sensor, and then like I would take the actual RPM at each and every instant of time, compare it with what is the desired value, and then take the difference, quantify the difference between what I desire and what is actually being obtained, take that error and pass it through what is called as a controller, and the controller will then adjust the electrical input to the fan, right. Then when that happens like we have what is called as closed loop control, okay. And closed loop control systems have feedback, okay. Feedback is a process of measuring variables that need to be regulated or controlled so that corrective action can be taken, okay. That is the process of feedback. So, consequently closed loop control what to say is more tolerant or robust to uncertainties that come in, disturbances and so on, okay. And typically what we called as during the design process unmodeled dynamics and so on, okay. So, but anyway let me qualify them, group them under uncertainties, okay, uncertainties, disturbances and all. But the flip side of closed loop control is that what to say the cost and complexity are higher, okay. So, in this particular course we are going to deal with closed loop control, okay. So, that is what we are going to deal with in this particular course, okay. So, let me just construct an example to just what to say explain what we did. Suppose let us say like we have let us say a DC motor, right. So, the DC motor is our system, okay, or plant. Okay. And to this DC motor, let us say I provide a voltage V of t as my input and omega t is my output. So, this is my input and this is my output. Suppose let us say I want a desired output, okay. Let us say a desired RPM of rotation, okay, from the motor. So, this is what we call as a reference input, okay. And what we do then is the following. So, suppose if I measure the actual output, then what I do is that I go and compare, then I take the difference between what I desire and what I measure, which is what is called as a error, and then let us say we pass it through an element called as a controller, and the controller then calculates what should be the input that should be provided to the DC motor. Okay. When the controller calculates the input that should be provided to the system, the adjective control is added to the term input. Okay. So, the input to the system becomes what is called as a control input. Okay. So, this is feedback. Okay. So, this is a typical layout of a closed loop control system with what is called as negative feedback. Okay. Okay. So, this is essentially closed loop control system with negative feedback. Why it is negative feedback? Because at the summing junction you can see that we are subtracting, like the feedback signal is subtracted from the desired reference input, right. So, that is why it is called as negative feedback. Okay. So, we are taking the difference between the reference input and the actual output, okay, and calculating the error. Okay. This is what is called as a closed loop control system with negative feedback. Okay. So, we can see that this is what we are going to essentially do in this particular course. Okay. So, some more terms that I want to say introduce here is that like this process of essentially taking this output measurement and feeding it back, giving it back is what is called as feedback. This is what is called as a feedback path. Typically, we can have a mapping in the feedback path. See for example, we can have some sensor dynamics coming into play here, right. So, let us say I use a sensor for measuring speed, that may have its own dynamic characteristics. I may need to use a filter to filter out noise, then a mapping comes in the feedback path. Okay. So, if a mapping comes in the feedback path, we call it as a when the mapping is not 1, we call it as non-unity feedback. Okay. So, when this mapping in the feedback path is 1, we call it as unity feedback. Okay. Like we will see how this affects our analysis later on, right. And many times when the controller provides calculates and provides a control signal to the system, it is typically realized by what is called as an actuator. See for example, let us say I have to essentially move say design a motion control system that essentially displaces a workpiece along one axis, right. Let us say simple translation of a workpiece in a machining system, right. So, let us say I want to regulate the position of the workpiece, right. I give a voltage signal to let us say an electric motor drive system which essentially provides translational motion to the workpiece, right. Suppose if a controller calculates that at this point of time provide 5 volts of input, right, to the electric motor, okay, or if it calculates and tells me that look, like provide, like 10 newtons of force to the workpiece, like to essentially move it by some distance x, right. So the controller may say provide 10 newtons at this instant of time, but then there may be a small what to say response time before the 10 newtons is actually realized in practice through the electric motor and drive system, right. So that if that is important, then we need to figure in what is called as actuator dynamics in the design process, okay. And sometimes like we can have disturbances coming into the system, right. Let us say like I have what to say sudden load that may come on a DC motor, right. For example, that I need to model as a disturbance and then like see how we can overcome such disturbances and so on, right. So one can see that we can add varying levels of complexity to this feedback path, okay, this feedback system, okay. We are going to study the basic feedback loop, like that is what we are going to do in this particular course, okay. And as we go along, maybe when we go to some case studies, we will add some more blocks, okay, and then see how the design varies, okay. To summarize, like what we are going to do in this course is the following, okay. So as a summary of all this discussion that we did, so the title of our course is control systems, right. So what we are going to do, what we are going to learn is the following, right. Closed loop feedback control of SISO LTI causal dynamic systems, okay. So that is what we are going to do in this particular course, okay. So that is the class of systems that we are going to do, SISO LTI causal dynamic systems, and we are going to do what is called as closed loop feedback control, right, of this class of systems, okay. And it so turns out that this class of systems, right, SISO LTI causal dynamic systems, the mathematical models that are typically used to characterize this class of systems okay, usually take the form of a linear ordinary differential equations, okay, what are abbreviated as ODEs with constant coefficients. Okay. So typically the mathematical models that are used to characterize this class of systems that we are going to study in this particular course take the form of linear ordinary differential equations with constant coefficients. Okay. So that is the class of equations that we would be focusing on. And another important aspect is that the kind of mathematical models we are going to essentially look at are what are called as spatially homogeneous. That means that we do not consider what to say variations of variables with space, right. So, we only consider temporal variations of variables. See, for example, let us say I want to analyze the variation of temperature of air in this room, right. So, obviously the temperature of air in this room can be different, like depending on the point where I am measuring and also the time at which I measure, right. So, but then what we do is that like we lump all the points in this room, that is the temperature of all the points in this room, into a single entity which essentially can be represented as a function of time. Okay. So, in a certain sense, like what we are doing is that we are lumping the effects, okay, as far as spatial variation is concerned, and we are going to assume that the entire room can be characterized by a single temperature which is only a function of time. Okay. So, spatially homogeneous means like we are essentially following sort of a lump parameter approach, right, towards modeling, right. So, spatially homogeneous, we are going to have what are called continuous time, dynamic, deterministic, mathematical models. Okay, that is the class of models we are going to use, right. So, essentially in a certain sense, like continuous time means like we treat time as a continuous variable. So, from pragmatic perspective, it just means that we are going to get ODEs, right, ordinary differential equations. Dynamic means we are going to have derivatives in the equations, like that is what essentially it means. It basically it represents. So, what is a dynamic model? It is something which explicitly considers future states of the system, right. So, and it essentially incorporates what is going to happen to the system in future, right, by incorporating derivatives of the variables. So, that is a dynamic model. Deterministic means we essentially neglect any stochastic effects. Okay. We do not consider variables as random variables, we consider all variables as deterministic variables, and we are going to have deterministic models. Okay. So, this is a class of models that we are going to use. So, in summary, like what we are going to do in this course is closed loop feedback control of SISO LTI causal dynamic systems using spatially homogeneous, continuous time, dynamic, deterministic mathematical models. Okay. So, that is what we are going to essentially learn how to do in this course. Okay. So, what we would subsequently do is essentially have a brief recap of what is the mathematical background that is required to do this analysis. Okay. So, that is something which we are going to learn, okay, which we are going to recap. It is assumed that some mathematical courses have already been completed before one comes to this particular course, particularly courses on complex variables, ordinary differential equations and Laplace transform. So, we would quickly recap some of these what to say tools and then we would move forward. Okay. So, that is going to be the plan of action, fine. Okay. So, thank you.